So the purpose of this video is to give you an introduction to how the differential method is used to determine the conservation of mass equation and then apply that to thermal fluid systems. So in the last video we talked about a variety of applications that were functional or useful for considering the differences between differential analysis and the integral method for considering fluid flow. So if we think of this wing here, or this airfoil, and then we consider a boundary layer growth across this, we have a certain profile of this boundary layer in here, and we can use differential analysis to describe this. So imagine that we had fluid flowing at this wing, and it would trace up. To recall, this would be the stagnation point. And then we would have streamlines that would converge over the top of this wing, implying by conservation of mass that actually the flow must accelerate. And that's partly the explanation for why we get lower pressure up top and thus we get lift. Now if we were to describe this system, we could have a whole bunch of differential elements in here, right? Very small boxes through which fluid would flow. And if we consider those boxes, right, make those boxes larger, well, we have a certain amount of fluid coming in and out, and we could then describe our changes in mass, our changes in momentum, and from that we could then provide an estimate for what happens with the airplane wing. So this differential control volume is the key to this whole analytical process. And we define it by dx, dy, and dz. So our differential volume then is defined as dx, dy, dz. We could also say that the amount of mass inside of this differential volume, so our differential mass, would be equivalent to our density times our differential volume. Now if our volume, if this deal is quite small, we might be able to say that rho is constant. We could also say this, so we could say this if dV is very, very small, or if we have an incompressible fluid. This isn't a great way of saying that. Let's say 0.1. It's very small. Not that it's much, much less than 0, but just that it's very small. So if we do the integral across this entire differential volume, we could then get a statement of the amount of mass that's inside of this system. And we can confirm that that is mass, right, by very quickly inspection. Density is kilograms per meter cubed times meter cubed. We have kilograms. As a result, we clearly have defined what the mass is inside of this volume. Now the thing to pay attention to right now, or one of the things I want you to pay attention to, is the fact that there are all these different faces, right? So there's a dx, there is a x face here on the right hand side, which is defined by dy and dz. So this is that face, dy and dz. It's the x face. We have an x face on the opposite side as well of this same cube. So this is going to become important because we have a certain amount of flow that comes into the system as in the x direction, and a certain amount of flow that goes out in the x direction. The next one is our y face. Okay, so a constant value for y And the area of that square is then defined as dz dx. And then we have a similar thing on the opposite side. But further in the y direction. And then last, we have our constant z faces, or planar, in the z direction. And this is defined as dx dy in terms of the area. So the area of a z face is always defined as dx dy. Now, our conservation of mass, we've talked about this a number of times in previous classes and now, is defined as the rate of change of mass stored within the control volume, or mass accumulated within the control volume. One easy analogy to think about this is like, say you had a tank that had a spout with water coming out of it, and you also had a faucet that was simultaneously filling the tank. And there's a certain amount of water in here. So we have mass m dot in, and we have m dot out, or at the exit. Well, if m dot in and out are equivalent to one another, then we're not storing anything inside of here, or we're not changing the amount that's being stored. However, if those are not equivalent to one another, then we might be accumulating more water inside of that tank. And that's what this equation that we see here, this entire equation, right, is all about storage. It's basically storage of mass and mass flow in and out of system. Now recall that the integral approach that we talked about in the last video for conservation of mass, it yields this equation down here at the bottom. Now this statement here is the rate of change of mass accumulating inside of that control volume, and this statement is the rate at which mass enters and exits the system. Now we're going to derive something that would give us the same, has the potential to give us the same answer, but in this case it's going to be differential analysis, not the integral approach that I'm showing right here. So let's think about this differential analysis approach again, okay? So what we're showing here, rho dx dy dz, what would that be? Well, we talked about it in a previous slide here just a moment ago. So our mass inside of that system, right, would be our density times dx dy dz. So kilograms per meter cubed times meter cubed is going to be equal to kilograms. So this statement here is equal to the mass inside of the control volume, inside of the differential element. Now what we need to show or recognize now is that the rate at which mass is accumulating inside of that system is then going to be a function of time. So if we say the partial derivative of density times our volume, we can get, actually let me rewrite that to be a little more accurate. We could say partial of time rho dx dy dz would then give us the rate of change of mass inside of the system with respect to time. Okay, so it would give us dt within the control volume. Rate of change of mass inside of the control volume with respect to time. Now we could also look at the rate at which mass flows across the control surfaces. On the far left-hand side, let's imagine that we have a certain density and of x velocity u. And then we're going to multiply that by the area over which that fluid is flowing in. Okay? So again, by inspection, we have kilograms, meters cubed. We have meters per second. And then we have meters and meters. We end up with kilograms per second. That makes sense. DTAMS. Makes sense. We have a rate of mass flow into the system. Now the thing we need to pay attention to here, the thing that gets a little tricky the first time you're seeing these differential elements, is that if you imagine that you are here on the left-hand side, and the velocity in the x direction is equivalent to u, what we describe here, by changing our x location, our velocity might actually change. So imagine that we were running through fluid through, say, a converging nozzle. Well, the fluid entering here is going to be moving slower than it is by the time it exits the system. So as a result of that, there is a du dx that is not equal to 0, right? So it increases. In fact, it's greater than 0. So to be more accurate there, let me say it's greater than 0 if, basically, this is the positive x direction. So we could see a similar thing within this control volume. And that's what's being expressed here. Is that in order to understand the amount of mass that comes out on the opposite side, we have the original rho u, which is expressed over here. But then we have to add in this rate of change of mass flow rate as we get a change in our x direction. So across dx, we have some change that potentially happened in our mass flow rate of fluid. We take a similar approach for the other surfaces. So in this case, we have our y direction. We have rho v, so density times our y velocity. But in this case, now we're doing dx dz, because we have dx dz is the planar surface that we're moving into. And then on the opposite side, we now have to account for the potential change as a result of moving in the y direction. And then again, we multiply by dx dz. And last, we have the z surface. So we are left with a certain amount of flow, or we have a certain amount of flow that comes into the bottom of the system. We multiply that by dx dy. So dx dy is the amount of area of that surface. And then on the opposing side, we've now adjusted for our potential gradient in velocity in the z direction, right? So potential change in the z direction. Okay, so conservation of mass here. What are we dealing with? If we take all of that stuff and we start combining it together, right? On one of the original slides, we had a statement that was, in fact, let me write it here. We had a statement that was dm dt within the control volume, right? Do you remember that? But in fact, that actually was a statement that said dt, or partial with respect to time, of rho dx, dy, dz. Now if you go back to those slides and consider what they all mean, and if you look at equation 17.2, so review equation 17.2 in the text and 17.3, you will see that the dx, dy, dz gets canceled in each term. Each term we cancel the dx, dy, and dz. They get divided out with the 0 on the opposite side. And as a result, what we're left with is this. We're left with d rho dt. So the change in density with respect to time. Now that's, when people first see it, it's not intuitive because they're not expecting us to express the change of density with respect to time. Your intuition would lean you more towards change of mass with respect to time. You've got to realize that that d rho dt, or change in density with respect to time, is actually representing change in mass with respect to time. And then we have our convective terms, so the rate at which mass gets transferred across the surface. And let me be more explicit with what I mean right there. So these three terms is the net mass, flow rate, exiting the control volume. So this is convective flow of mass flow rate across the surfaces of the control volume. And then this term here, d rho dt, is the rate of change of mass stored in the control volume. So say like accumulated inside of the control volume. Now as a quick comparison, right, this is the integral method that we talked about in the previous video, and I do want to provide it up here just as a reminder, because this statement here, this first term, is the rate of change of mass stored in the control volume. Well, that sounds familiar. And this is the net mass flow rate exiting the control volume across the surfaces. That also sounds familiar. So you need to recognize, right, that the differential method and the integral method in many ways are actually expressing the same thing. They're just approaching the problem from different perspectives. Integral method, right, we would be drawing a large control volume around a device or an engine or whatever it might be, and then we would be considering how the flow enters and exits that system. Differential element method, we would be, right, defining these really small elements that we would then be using to basically describe the flow throughout the entire velocity field. So a couple things here real quick just to make sure it's clear. This is equation 3.13 if you want to track it down. It's also at the beginning of chapter 17. And then we have, this is equation 17 4a. I kind of drew those together there. That's equation 17.4a. All right, a couple quick comments and then we'll close out here in terms of simplifying the continuity equation. So there's an alternate method of writing this differential equation, and that's called vector notation. Vector notation actually allows in many ways to simplify a lot of this writing, which you'll see here right now. And this is a del operator. essentially an expression that we have d dx plus d dy, and I should put little brackets here, plus d dz, or I shouldn't be saying d's, those are partial derivatives. And you'll notice, right, that we then have, we would be plugging in, say, density times our velocity component in the z direction. This is a very useful method for writing out differential equations, so please be aware of it going forward. So if we were to define this equation as being steady flow, we could simplify down to an expression that would look like this. Is equal to 0. If we then said we had an incompressible flow, we could simplify further, because now our density would not be a function of x, y, or z. So rho is a constant. Therefore, density is not a function of x, y, or z. So we could get a statement that we would say the partial of u with respect to x, partial of v with respect to y, and partial of w with respect to z are all equal to 0. And then last, if this were, let's say, a one-dimensional flow, then this whole thing could simplify down to, say, du dx is equal to 0 if it's one-dimensional. With that, we'll close out. We'll cover some additional opportunities for understanding continuity and conservation of mass in some additional study guides that are available on Blackboard. If you've got any questions, of course, you're welcome to reach out to any of your instructors at any time.